Hello and welcome. I'm Alex, the Industrial Engineer. Today's video is the second part in a series on operations scheduling. Today's video topic revolves around two resources scheduling type problems and is the logical next step up from single resource scheduling shown in part 1 of the series. If you have not seen part 1, I recommend starting there to really grasp the basics of operations scheduling, but it is not essential to understand today's video. Part 3 of the series will cover problems when there is scheduling to be done on more than two resources. Today's two resource scheduling video will cover the difference between parallel, sequential, and job shop process scheduling. We'll go over Johnson's rule and into a brief offshoot into how to analyze problems from a stochastic perspective. This brings us back to our first bullet point of defining the difference between parallel, sequential, and job shop problems. Parallel processes means you have two identical resources to process jobs. So each job can be processed by either resource. And what this means is, let's say we have our 5 jobs here, A, B, C, D, and E. With parallel machines, in our case, we have machine 1 and machine 2. All you want to do is split the jobs in half and assign them to either machine, since they are identical machines. Now, sequential processes means each job moves from resource 1 to resource 2. Think of this like an assembly line. So let's just say we choose job B to go first. That means job B would start at machine 1 and then go to machine 2 and then leave. And then same thing, all these jobs follow the same route. Now imagine some jobs do not need to be processed by both resources or both machines. This would be a job shop type problem, where each job has its own required path throughout the processing area. We have an example here. We have job A, which only needs to be worked on by machine 1. Then we have job B, which has to go from machine 2 to machine 1, and then it's done. So every job has its own unique path, and this is where two resource scheduling gets the most complicated. And we'll further explore the discrepancies between each of these throughout today's video. First, we'll dive into an example on parallel processes. The question reads, an incoming batch of 5 jobs is to arrive later this morning. There are 2 identical machines available to process the jobs. Given the processing times for each job in the table below, determine the optimal job schedule that minimizes the make span and mean flow time. So in what order would you schedule the jobs to be completed by the machines? Before we can really answer that question, we need to determine what makes a sequence good. On the left-hand side here, I have 3 random sequences that the answer could be, but how do we know which one is better than the other? If you recall from a single resource scheduling, there were a variety of performance metrics that you can calculate for any given schedule. These include the average tardiness, the maximum tardiness, number of tardy jobs, the mean waiting time, mean flow time, and the make span, as we have here. Now, the make span in single resource scheduling, part 1, was always constant. However, in two resource scheduling, the make span is different for each schedule and is the leading performance metric used to compare schedules alongside the mean flow time. The make span is simply how long it takes to complete all jobs, and the mean flow time is the average time it takes to complete jobs. Now that we have read the question and learned how to evaluate sequences, we will work through how to solve a parallel processes job scheduling problem. The algorithm I'll teach today has us place jobs in descending order by processing times, and we'll schedule these jobs on the first available machine. And then at the end, we'll flip the machine sequence. This might sound a little complicated just reading, but we will dive into how to do this. First, we'll order the jobs by their processing times in descending order. So if we look at our given information over here on the right-hand side, we're going to look for the largest number, that would be B. And then we have A, and then D, C, and E. So this is the order we're going to schedule on the machines. So We're going to do job B first, and we'll just throw it onto machine 1. And we've had this filled out on the next slide. So job B takes 30 minutes. And now we schedule job A on machine 2 since it has the smallest make span so far. So right now the make span of machine 1 is at 30, and we're still at 0 for machine 2. So that's what it means when it says schedule on the first available machine. We're going to put A down here. And now job D will also go on machine 2, and we'll just fill out this schedule. And here we have completed scheduling jobs on the 2 machines. Notice these numbers by the jobs are the cumulative timestamps. So this does not mean it takes 48 minutes to complete job C. It's total. So job B was 30 minutes, and now job C was 18 more minutes. So the mean flow time or the MFT and the make span, or MS, as we have down here, those were calculated based on these timestamps. Remember, the mean flow time tells us on average how often jobs are completed throughout the schedule. So it's simply an average of all of these timestamps. And the make span is the total time it takes to process all jobs. So that is the maximum number, which is this 55 here. We are required to now flip this sequence on the machines. This is not flipping the letters up here, because otherwise we would just do that in the first place. We are flipping the machine schedule down here. And I'll kind of flip back and forth so we can see that. So you see on machine 1, we go from BC to CB, and then machine 2 goes from ADE to EDA. And what is the point of this flipping? Well, if you notice, the make span, or the MS, stays at 55, but the mean flow time gets greatly reduced. It goes from 40.6 to 32.2. Why does this occur? Well, since we first scheduled the jobs in descending order by processing times, the jobs that take up the most time were split evenly amongst the machines. So we scheduled jobs A and B first, because those have the highest times right here. Furthermore, we know from the SPT, or shortest processing time preset method from the previous video, that completing jobs with shorter processing times first minimizes the mean flow time on a single machine. And this translates here to the 2 machines. Notice how we complete more jobs sooner. So at timestamp 18, we have 10 and we have 30. If we go back, we see that we have 30, 25, 45. These are just larger numbers. And so this is our final answer to the question. Machine 1 will complete jobs C and B, and machine 2 will complete jobs E, D, and A in that order. And this algorithm can be effective on more than 2 parallel machines as well. Now let's take a step back and discuss the difference between deterministic and stochastic problems. This is a very important topic, and not just within industrial engineering. A deterministic problem is like the one we just solved. We assumed that the given processing time, or remember this table? We assumed these numbers were constant and known with certainty. However, in reality, we know that this is not how it works. Let's take job A, for example. Maybe the employee working on job A is interrupted by a coworker, or they make a mistake and need more time to correct it. Then our assumption of 25 minutes is wrong. The real world is full of this inherent variability. A stochastic approach addresses this problem, where the input parameters are made variable to more accurately mimic the real world with its variability. For example, let's keep looking at job A. Say in the past, we have worked on jobs either identical or similar to job A. And we can leverage this historical data to get a more accurate picture of how long it takes to process job A. So over here on the right-hand side, this is some historical numbers on job A. We have our 25 minutes here, but in the past, it's taken 32 minutes, 18, 27. See, it's all varying. And so how do we use this additional information? Well, from the historical data, we can calculate the mean and the standard deviation. so that we can model job A processing time as a normal distribution. And let's draw what this looks like in comparison to the deterministic approach. So deterministically on the left-hand side, kind of have a weird graph. It would just be the number 25 every time. It's a constant number. If we go to the stochastic side, that same job will follow a normal distribution where the center is the mean, 25, and we have a standard deviation of 5. So I'm going to go out about here, and this will be 15 and 35. And the reason I know this is 15 and 35 is 2 standard deviations away from the center. That's where 95% of the numbers occur. This area here is 95% of the curve. And so what this means is that job A can take on any number under this curve. And as you see, the closer you are to the middle, the more likely that number is. So we're still likely to get a number close to 25, but it's possible to be at one of the extremes of 15 or less, or 35 and above. While this still may look complex, I hope the applied example in Excel will better showcase the power of the stochastic method. Here we are in Excel. I inserted the same given information from the deterministic approach in the upper left. However, the difference now is the addition of these standard deviations for each job. Remember, we calculated a 20% standard deviation for job A, and for the rest of the jobs, I filled in random standard deviations. The original processing times will become the mean of their own distribution. Remember, using the mean and standard deviation, we have a normal distribution that each processing time now follows. Notice when I update the sheet, the sampled processing times, if you take note of these numbers here, these will become variable, while the original deterministic times will remain constant. You'll see the difference between deterministic and constant here, or stochastic. So when I update the sheet, we can see those normal distributions, that curve being sampled. So we can look at job A. We drew a picture of that earlier. There's that 35. That's a pretty rare one to see. But these will all be kind of close to 25. And now this sheet solves the same problem as before, where we order the now sampled times in decreasing order, so largest to smallest. And Excel finds this for us. Then the machine schedules are made, and then it's flipped down here. So this would be our final answer, this flipped schedule, with the make span and mean flow time being calculated from that. This flip schedule, again, minimizes the mean flow time, but keeps the same make span. See, these make spans are the same numbers, but the mean flow time gets reduced. Hope you're following along with this so far. All I have changed is the fact that the given information, so this processing time, is now this column. So that's all I changed in the problem, and I did the same algorithm we learned in the slideshow. Now that I've changed the inputs, let's look at the make span and the mean flow time. Every time I update the sheet, these numbers will also be variable. This makes sense, right? So now you may be thinking, which outcome is the final answer? What job sequence do we use? Another name for this approach of solving problems is Monte Carlo simulation. Given that our problem is now stochastic, we can calculate this make span across, say, 1,000 trials and find the job sequence that occurs the most often. So we're going to look at this, and we're going to update our sheet 1,000 times and find the sequence that occurs the most often. And this will be our answer. Now, to complete the Monte Carlo simulation, I wrote some VBA code to do this for me. Let's sit back and watch the computer calculate the make span and mean flow time 1,000 times. Okay, and these results were recorded on a separate worksheet down here. So here are all 1,000. I'll quickly go to the bottom and show you. Here we go, all 1,000. Now recall the deterministic mean flow time from the slideshow was 32.2 minutes. from the simulation, the average mean flow time was lower at 26.29 minutes. Now, to wrap up this stochastic analysis, what is the job sequence we recommend using? What is our final answer? If you also remember the deterministic answer, the sequence was BADCE. This was before flipping. But from the simulation, this same sequence occurred only 20% of the time. So we can't confidently say that this is the correct answer quite yet. In the deterministic analysis, this would be 100% because the numbers don't change. We have 20% of the time. So let's create a pivot table based on our 1,000 trials data to compare the most frequent sequences that occurred. And now I'm going to filter the top 3 sequences. And here we have it. So remember the deterministic, I'll zoom in here. The deterministic answer was BADCE. This occurred 200 times. Remember, that was a 20% chance, 200 over 1,000. And we also have 2 other popular sequences that occurred. But our final answer to the question would still be the same answer from the slideshow, just because it occurred most often. And this sequence minimized the make span and mean flow time the most often throughout our 1,000 trials. So this will be our final answer, BADCE. And now for an example on sequential processes. The question reads, an incoming batch of 5 jobs is to arrive later this morning. Each job must be processed in order from machine 1 to machine 2. Given the processing times for each job on each machine in the table below, determine the optimal job schedule that minimizes the make span and mean flow time. So this is the same exact question as before, but we have different numbers for each machine because these are unique machines. They don't do the same thing anymore. And jobs must be processed from machine 1 to machine 2. And to solve sequential process scheduling with 2 resources, Johnson's rule is used to find the optimal schedule. So to apply Johnson's rule, you must present your data just like we have it here. And so we must find the smallest time within the 2 columns. If this smallest time appears in the first column or machine 1 column, we're going to schedule that job first. If it appears in the second column, we're going to schedule that job last. I'm going to repeat this algorithm, and we're going to repeat this rule until it's finished. Okay, so let's implement Johnson's rule ourselves. We already have our information in the format needed. Now let's find the smallest number in this table. Looks like it's going to be at 10 right here. And so we found this 10 in the first column. That means we're going to put E right here. We're going to schedule it first. And now we can get rid of E and we'll continue the process. We'll find the next smallest number. Looks like that's going to be 13. And so since we found this smallest number in the second column now, this will be scheduled last. So job C will go last. Now we can cross that row out. And this continues. So when next we find 15, that's in column 2. So job A will go here. And we'll cross out A. And now we find 20 in column 1. So D goes here. And we have 1 job left. So we'll put B in the middle here. So this is our job schedule from Johnson's rule. Now that we have our schedule, let's see what this sequential process looks like on the 2 machines. So first, we schedule job E. All of these jobs must go from machine 1 to machine 2. So we have this 10 number from the table and 28 on machine 2. And so it takes 10 minutes on machine 1. And then after that's done, right here, it takes 28 additional minutes now to get to 38 here. And so this continues. Then we go E, D, B, A, and C. So here's the complete schedule. The make span is 142 minutes, or 2 hours and 22 minutes, which again is the time it takes to complete all jobs. It's also this number down here. And the mean flow time was calculated to be 78.3 minutes. Johnson's rule gives us the optimal schedule. So these are the lowest values for the make span and the mean flow time you will find in all possible sequences. Now, lastly, we have an example regarding job shop type problems. The question reads, an incoming batch of 5 jobs is to arrive later this morning. Given the processing times for each job on each required machine in the table below, determine the optimal schedule. Now notice in the given information table, each job has its own unique path. And we saw this earlier at the beginning of the video. And some jobs only need to run through one machine to be completed, others 2 machines and in different directions. If this seems complicated, it's because it is. Just think if there were 2 more columns or 4 machines. So we have machine 3 and machine 4. We could have all sorts of paths going on this table. And then they can go over here. There's a plethora of paths when you add additional columns. Now, this type of problem becomes easier if you enforce sequential completion of jobs, as shown in the previous problem. So I'm going to use these 2 incomplete job schedules to show how enforcing sequential processing of jobs makes the problem easier. Here at the top, we have the sequential jobs constraint activated. This means that, again, job A1 or job A on machine 1 must come after A2 no matter what. At the bottom, we relax this constraint, and this means we can fit any number of jobs in between A2 and A1. So, for example, I just placed C1 in between. When you allow this to happen, there's a lot more permutations possible for schedules. So, on top, when we have this constraint, we know that there are 120 unique schedules possible, or the number of jobs factorial. So we have 5 jobs. That would be 120. On the bottom, notice how there would be a lot more than 120 because we can fit any number of jobs in between the jobs that take 2 machines. Just due to the complexity of the problem, we often turn to computers to determine the best schedule for us. Using algorithms such as Tabu Search, the genetic algorithm, and simulated annealing, we can derive near optimal or optimal schedules. The specifics of these algorithms will not be explored in today's video, but I wanted to make you aware of their existence as potential tools to solve complex problems. So I had ChatGPT write me a Tabu Search script with the same given information you see in the upper right hand here. In short summary, Tabu Search will jump around the sample space, trying out different combinations of ways to order the jobs, and attempt to locate the best schedule. The algorithm cannot revisit the same sequence as it already had, so it'll search the sample space really quickly. All right, so I run Python code using Visual Studio Code or VS Code. Again, I had ChatGPT write the bulk of this code for me. And if you attempt to do the same thing I have here, know that ChatGPT can make mistakes, so it is helpful to know how to read and understand the code being used. And this, again, is the Tabu Search algorithm. So we have 140 lines of code. And it does its best to jump around the sample space, testing unique schedules in an attempt to find the schedule that minimizes the make span. And after a certain number of non-improving solutions, it stops searching and returns the schedule it found last. So let's run the program a few times and see what outcomes we get. This usually runs pretty quick too. And here we go. So this program outputs the machine schedule that we were using throughout the video. And in the output here, the terminal, we see it gave us a make span of 94. And that was with the schedule A, B, D, E, C. You can kind of see we have the sequential rule enforced here. Job A, here's A2 to A1, and then here is D1 to D2. Let's run it again and see what we get. We got something similar that time. I want to show an example where it's different. And here we go. So this time the Tabu search algorithm was jumping around, but it couldn't find the schedule that gets a 94 make span. So it stops searching. And here's the schedule that gets 107 make span. So I just wanted to show you the Tabu search algorithm, just so you know it is a tool available to solve such complex problems. And in the next video, we'll dive into the genetic algorithm to solve problems with greater than 2 resources. All right, and that is the end of today's video. I thank you for watching. And if you could please leave a like and subscribe and comment for any future content you might want to see, I would greatly appreciate it.